Hey everyone, today we are going to be jumping into related rates. And so this is a problem you are pretty much guaranteed to see on the AP exam. So we really want to get into these and make sure we understand how to handle these different types of problems. So let's talk about what a related rates question is, what it looks like. Okay, so it says in the real world, the rate at which one variable changes can directly affect the rate at which something else changes. Right? So a few examples. It says if the radius of a pumpkin gets larger, so let's say we have a pumpkin here. Here's my pumpkin. Looks like a tomato, but that's okay. If the radius of a pumpkin gets larger, so we're talking about our radius here. If I were to look at a pumpkin whose radius got larger, then I know the volume of the pumpkin will also get larger. So the rate at which those things change are related to one another. Okay, another common type of problem. If a ladder slides down a wall, so let's say I have my wall here and here's my ladder. So if my ladder slides down the wall, so there's my ladder sliding down, and the base of the ladder is getting farther away from the wall, then the height the ladder reaches on the wall will decrease. So there we've got a few things changing. We've got the rate at which it's sliding down, the rate at which it's sliding away, and then the rate at which the height it reaches is changing. So we're just talking about how the rate that one variable is changing affects other variables. And so one thing I want to make a note of here, we're always talking about the variables changing with respect to time. So since the variables are changing with respect to time, that means we're always going to be differentiating with respect to time. And since that's the case, when we're differentiating, we're always going to be using implicit differentiation. So implicit differentiation is going to be a big key of working out these derivatives. So the first couple of problems here just give us practice with finding these equations. So relating the variables and then finding their derivatives using implicit differentiation. So our first question says, assume that the radius r of a sphere is a differentiable function of time, t, and let v be the volume of the sphere. So find an equation that relates dv dt, so the derivative of volume with respect to time, and then derivative of the radius with respect to time. So the first thing we need to do is find an equation for the volume of a sphere. And so we know that volume is 4/3 pi r cubed. So that's just the equation of the volume. Now it wants us to find an equation that relates dv dt and dr dt. So I'm going to differentiate this. And again, I'm differentiating with respect to time. So my derivative of volume with respect to time, I'm going to differentiate this normally. So I'm going to get 4 pi r squared. But now since I'm differentiating with respect to time, I need to add on a dr dt. That's the implicit differentiation piece. So that would give me my equation relating dv dt to dr dt. Okay, our next problem says assume the radius r and height h of a cone are differentiable functions of t, and let v be the volume of the cone. So here's another formula I need to know. So now I want to relate all these variables, dv dt, dr dt, and dh dt. So first, let's find the volume of that cone. I know that's 1/3 pi r squared h. So it's 1/3 the volume of the cylinder with the same radius and height. Now, this one is a little tricky. We have to be careful here because we need to use product rule when we differentiate this, as I have essentially this piece and then my function of h. So I'm just going to simplify this a bit. I'm going to pull my constant together. So I'm going to do pi over 3 r squared h. And now I'm going to go ahead and differentiate. So my derivative of volume with respect to t, I'm going to do pi over 3 r squared times the derivative of h with respect to t plus h times the derivative of pi over 3r squared with respect to t. So I'm going to get times 2 pi over 3r, and then I have dr dt. So it looks a little bit messy, but that'll give us our equation that relates dh dt and dr dt to dv dt. So the next thing we're going to do is actually dig into some related rates problems. And we're just going to go through an overview of how this is going to work. So I'm going to give you some steps on page 8. And I'm actually going to change the order of these. I tend to do it a little bit differently than this order. So we'll make a few changes here. But the first thing I definitely do, we're always going to draw a detailed and labeled picture. Now, here's something that's going to be key. So I want you to star this, underline it, whatever you need to do. I am not going to put any numbers in my picture unless they're going to be constant. And so we'll talk about what this means more when we look at some examples. So no numbers go into my picture unless they're going to be constant. They're never going to change. Now here's where I vary a little bit, is in the middle here. So I'm going to scratch these out. The next thing I like to do is actually step 2. And I like to write an equation that relates the variables. And so our hint here is to think geometry formulas. And we'll actually be using the space below to kind of keep track of formulas as we go through more and more problems. Because again, these are formulas you're going to have memorized. These will not be provided for you. Okay, so we're going to write an equation that relates the variables. Then we're going to take the derivative of the equation, and I'm going to add with respect to time t. So that's essentially what we were just doing on the previous page, was practicing writing the equation and then taking the derivative. The next thing I'm going to do is list the variables and their derivatives. So list those pieces that come out of step 3 and then fill in any values that we know. And then our last step is to solve and make sure our answer has units. So we'll kind of be referring back to these steps as we go through. For right now, I'm going to leave this common formula space blank. And what we'll do after every time we go through a new set of problems is add any new formulas that we've come across. So let's go ahead. This first day here, we're going to focus on Pythagorean theorem problems. So these are all going to use the Pythagorean theorem. So actually, let's go ahead and put that here, since it's a major type of problem we'll be working with. Okay, so here we have our a squared plus b squared equals c squared. So let's do 3 problems, see how this looks. So our first problem, an airplane is flying towards a radar station at a constant height of 6 kilometers above the ground. So let's see, if the distance s between the airplane and the radar station is decreasing at a rate of 400 kilometers per hour when s equals 10 kilometers, what is the horizontal speed of the plane? So let's take a look at this here. One disclaimer is that I am not an artist, so my drawings will not be totally pretty. Just Please don't laugh too much. So here I have an airplane. It's probably more like a flying whale, but you get the idea. There's my airplane. Okay, and it's flying towards a radar station. So what we actually have is something that looks like this. All right, and here's my radar station. It's going to be a house. That's about the extent of my capabilities. Okay, so it's flying towards, so I know it's flying this way. Flying towards a radar station. Now this is important. It's at a constant height of 6 kilometers above the ground. Now, we said over in step 1, we were going to draw a detailed picture. We were not going to put any numbers unless they're constant. Well, here I know that height above the ground is constant, so I'm going to go ahead and label this 6. And again, I'm only doing that because it stays constant. So now I have, let's keep reading, if the distance s between the airplane and the radar station. So the distance between the airplane and the radar station is going to be this distance here. And then I'm going to call this x, because it doesn't define a variable for me. So there's my picture. I've got a right triangle. I've got a horizontal speed of x. The distance between the plane and the radar station is s, and then a constant height above the ground of 6. So now I know I can relate these 3 values using the Pythagorean theorem. So I have x squared plus 6 squared equals s squared. So there's the equation that's going to relate those values for me. So now we've done step 2. We've written an equation that relates the variables. So then we said step 3 was take the derivative with respect to time. And again, that's going to be implicit differentiation because I'm differentiating x, but with respect to t. So I'm going to take the derivative of x squared, which is 2x, but then I need to add on my dx dt because I'm doing this with respect to time. 6 squared is just 36. That's a constant, so its derivative is 0. So I have equals, my derivative of s squared is 2s, but then I have ds dt. So really here, if we're keeping track of our steps, step 1 was drawing the picture. Step 2 was coming up with our equation. And now step 3, we've taken the derivative of that equation with respect to t. So now, step 4, we said to list the variables and their derivatives. So in other words, here's what I want to do. I want to look at this equation and pick out what I need to know. So I know in order to solve this, I need to find something out about x. I need s. I need dx dt. And I need ds dt. Now, 3 of these hopefully I know, and 1 of them will be our unknown that we're solving for. So let's see what we know. So let's see, this constant height of 6 just helped us to form our equation. Now, it says if the distance s between the airplane and the radar station is decreasing at a rate of 400 kilometers per hour. So, if we're talking about this distance and the rate at which it's changing, that's going to be our ds dt. This tells me the rate of change of s. And since that is decreasing, we have to make sure that we have that as a negative rate of change. So I'm going to grab a highlighter right here. Since that rate is decreasing, we have a negative rate of change. So it's decreasing at a rate of 400 kilometers per hour when s equals 10 kilometers. Then it wants to know what is the horizontal speed of the plane. So ultimately what we're trying to find is dx dt. Now, it seems like we have a little bit of trouble here because I know this is my unknown. I know 2 of the values, but I don't know x. However, since we're finding this at the point when s equals 10, I know that when s equals 10, I look back to my formula and I have x squared plus 6 squared equals 10 squared. So now if I simplify, x squared plus 36 is 100. I have x squared equals 64, or x equals 8. So now I can go back and plug that in. So now I have everything I need to plug into my formula and solve for dx dt. So I have 2 times x, which is 8. dx dt is what we're trying to find. And that's equal to 2 times s, which is 10, times ds dt, which is negative 400. So now we're just going to solve. I'm going to have 16 dx dt, and that's going to be equal to negative, 8,000. Okay, so now I know dx dt at the time when s equals 10 is going to be, what does that give us? Negative 500. And my units, we have kilometers per hour. So that is the horizontal speed of the plane. Okay, and so what that negative means is that speed, that horizontal speed, that distance is decreasing, which gives us a negative rate of change here. So I know that's a lot to take in. I think we'll do one more, and then we'll use actually the third example to go over in class tomorrow before you get some time to practice. So let's do one more just so you can see another example. These ladder problems that we're going to do next are very, very common, so I want you to see that, and then we'll get lots of practice tomorrow. So here we go. What we have is a 6-meter ladder is against a wall. So there's my wall and my floor, and I've got my ladder. So now I want to label. So I'm going to use x to be the distance along the floor, y the height along the wall, and now I'm going to label this 6 because that ladder, the length of that ladder is not going to change. That's our constant. So it's okay to label that in our picture. So now I know that the formula that relates these three values is going to be x squared plus y squared equals 6 squared. So again, if we're thinking in terms of steps, my first one was the picture. Second one is an equation that relates them. So now we're going to differentiate. So let's see, if I differentiate, I get 2x dx dt plus 2y dy dt, and that's just going to be equal to 0. So now again, for step 4, I'm going to pull out all the variables that I have here and derivatives, and we're going to see what we know. So I know I need an x, I need a y, I'm going to need dx dt, and I need dy dt. So let's go back and read and see what we've got. It says the bottom is pulled away from the wall at a rate of 1/2 meters per second. So if I'm talking about being pulled away from the wall, that's this x here. That's going to give me dx dt, the rate that this is changing. And since that distance is increasing, that's going to be a positive rate here because this distance is increasing. So I know that, and I want to find how fast is the ladder top sliding. So in other words, what's dy dt when it reaches 3 meters up the wall. So in other words, when y is 3. So now again, we need to go back and solve for x. So what we know is that when y equals 3, we have x squared plus 3 squared equals 6 squared. So x squared plus 9 is 36, or x squared equals 27. So x equals the square root of 27. So I'm going to plug that in here. So now we have all the values that we need to solve for dy dt. So now we'll do what's really step 5, which is to solve. So now I have 2 times the square root of 27 times dx dt, which is 1/2. Then I have plus 2 times y is 3 times dy dt, which is what we're trying to solve for, and that's all equal to 0. So now our goal is just to solve for dy dt. So I can simplify this. Let's see, I get 6 dy dt equals, I'm going to move this over, a negative root 27. So now, sorry, I'm getting squeezed in here, dy dt equals negative root 27 over 6. 27 is 9 times 3, so this is negative 3 root 3 over 6, which is negative root 3 over 2, and our units will be meters per second. So that's the rate of change. That's my dy dt. And again, this negative accounts for the fact that the ladder is sliding down the wall, so that distance is getting smaller. And that's why we have a negative rate of change. So I think that is more than enough for today. Tomorrow we'll do number 3 in class, and then you'll have time to practice this. So hopefully you're not feeling too overwhelmed. I think it'll start to make sense the more practice you do with it.